Welcome to my YouTube channel, which is dedicated to the learning of the applied mathematics in structural analysis. In this video, we will take a look at the application of Laplace transforms and to use it to find the elastic curve or deflection of the beam, which has a fixed support at one end and simply supported at the other end. As you can see, this beam is a statically indeterminate beam because it has three unknown variable or forces RA, RB, and MA, while we only have two static equilibrium equations. The sum of the force, vertical force, equals 0, and the sum of the moment bending at point A is 0. So two equations but three unknown, so that cannot be solved. That's why it's called statically indeterminate beam. So in this example, we will try first to find the reaction force RA, RB, and MA, and then we will try to find the equation of the elastic curve, the beam deflection, using Laplace transform and its inverse. And then, once we know the equation of the elastic curve, we will try to test if A equal L, then we will try to find what will be the maximum deflection, and we will show that the maximum deflection when A equal L is at the position of x equal 0.5785. And then lastly, we will do the visualization by plotting the beam deflection for four conditions of the loading as shown below. A equal a quarter of the length till A equal L. But before we do that, we need to use a unit step function to express the load for this beam, because it's not continuous, because the load will be 0 if x greater than A, but if x between 0 and A, then the load is key. So we will introduce and use this unit step function. So we will say our loading as W as a function of x. The value will be Q if x is between 0 and A, and the load becomes 0 if x greater than A. This can be written in terms of unit step function. So we have it here. This will do the trick because we will express the loading Wx as Q with this unit step function. So 1 minus 0 is 1, so the value will be Q, because there will be for the load will be, this value will be always be 1 if because x greater than 0. And then if x greater than 0 is 1, and here it means x greater than A also 1, minus 1 is 0, so it meets this condition. So we can express the load in this expression or equation W as a function of x as Q of this unit step function. The differential equation for the beam is the fourth derivative of the deflection of the elastic curve, and this is equal to the our load Wx. Now we need to take the Laplace transform on the left hand side, the fourth derivative, and also on the right hand side, and this loading Wx is expressed in the unit step function. So we need to do the Laplace transform left hand side and right hand side. So from the books of Laplace transform, you will find that the Laplace transform for the unit step function or of the heavy unit function is as shown here, and Laplace transform of 1 is 1 per s. And then before we continue, we will introduce the Laplace transform of derivative. So we will use this symbol to simplify our discussion here. So the first derivative we can say as we can express as y with the first quad. Second derivative is y with the second quad. The third derivative is y with the third quad, and so on. And let's say that the Laplace transform of y is L, y, big capital, and then the Laplace transform of y is y in the lowercase. And assuming all the derivative are piecewise continuous, then we have this Laplace transform for the derivative that you find in the book. The first derivative, second derivative, third derivative, and fourth derivative. This is the one that will be used on the left hand side for this to express this fourth derivative as Laplace transform. And here will be, if you are interested in general formula, if you need to find a Laplace transform for the derivative higher than the fourth order, for example. Now, taking the Laplace transform of equation 1 here, Laplace transform of fourth derivative and of the root expressed in the unit step function, we will get this Laplace transform. Now, applying the boundary condition, as we know that point A is a fixed support, so the deflection should be at x equals 0 should be 0, and the rotation at point x equals 0 also 0, so we can remove these two variables from there. Then it reduced to become this equation, where C1 is equal second derivative and C2 is equal to third derivative. So we have this expression or equation. Now, how do we find back the elastic curve y, the big y here as a function of x, the elastic curve? Then we have to do the inverse to find the back, because now we have the Laplace transform. Now we want to get back the original function. Then we do the inverse of the Laplace transform of this, then we get this result, and this is the unit step function. So it means if x smaller than a and become 0, so this side will be gone. This is how can be written as follow. So this part is gone, x minus a, the unit step function, because the value is x smaller than a, and if x greater than a, then you will see this part. How do we find the C1 and C2? Now we can apply, we have two equations now, with two unknown. Then we can apply the boundary condition at point B, where the moment bending at the simply supported beam at the right hand side here, when x equal L should be 0. Then we get this. And the other boundary condition at point B, the deflection y at the x equal L should be 0. Then we get this equation. So we have two equations, 2 and 3, with two unknown constants C1 and C2. And we can resolve the equation to get the value C1 and C2. Now substitute this C1 and C2 back to the here, this equation, then we get this. Now to simplify the formula, we can take n equal b divided by L. Go back again here, you will see that. So this is the A, this is the B. A plus B equal L. So A is equal L minus B, or B is equal L minus A. So we can express the formula of the elastic curve. This for apply for this ranges x between 0 and a, and the other part for x between a and L, where n is equal b divided by L. Now we can find the support reaction forces MA, RA, and RB. So MA is a second derivative of the elastic curve. So we already have the elastic curve, then we can find the second derivative is EI, the modulus Young and moment inertia, and multiply by C1. So we get this value. Now we can simplify, taking N equal B divided by L. B is L minus A, so we get, and we define A divided by L as N. Then we can simplify the formula and find MA equal this amount. Now we know that N moment, fixed N moment support MA. Then we can find the reaction force, vertical force at point A, RA, by using static equilibrium equation. Then we get this value. And then to get RB, we can simply use another static equilibrium equation that the sum of all vertical forces should be 0. Then we get RB. Now we have our deflection for the beam. Then we can take, if A equal L, then B become 0 and N become 0, because as you remember here, A equal L, B is 0, and N equal 0, and is B divided by L. Then we can simplify the equation for the deflection. Then find the maximum deflection of this. We can take a first derivative of the equation and set it to equal 0. These are the, in calculus is where we want to find the maximum and the minimum value. Then by solving the quadratic equation, we get the value x. Here we need to choose the minus 1 because the positive one will be bigger than L, but our beam is with the domain between 0 and L. So this will be the x that we use to find the maximum beam deflection, and substituting this x value back to the equation, we will get the maximum deflection as this, and this is a downward, minus. Now we can plot the visualization for various loading for this case of a loading, and you will find it here. So now let me go directly to the simulation here. For the visualization, you will find that this is the load case number 1, number 2, number 3, number 4. And remember, for the load case number 4, where A equal L, the maximum is at 0.5785. So that will be here. So the plotting really show where is that location, and this is really the maximum. And with this visualization, you can easily change the line. Let's say line number 3, you can change the color, put into the other color, you can change it, and then you can even change the symbol here and choose the other one. So you can play around to see the color and the symbol that you want to use to illustrate when the loading is equal 25% of the length, 1/4, half. This is 75%, and this is A equal L, and the maximum bending is, and the maximum deflection is at the point 0.5785. That's it for today. Thank you for watching.